Bounded sets are always totally bounded. That's false. That's kind of a weird little counterintuitive thing here. A totally bounded set is bounded. But a bounded set does not have to be totally bounded. You have to, you want to see that? Okay. There's a space called little L2 that consists of sequences. So you would have sequences of terms AN, and the ANs are real numbers, and the sum from n equals 1 to infinity of the AN squared converges. This is called Hilbert's sequence space. And this actually is a vector. I've written it as a vector. So an element might be 1, 1/2, 1/3, 1/4, right? 1/2. If I square these and add them together, I get pi squared over 6, right? Pi squared over 6 is less than infinity. So this infinite dimensional vector would be in the space L2. This is one of the classical function spaces that was investigated about 100 years ago by Rees and his buddies. You'll see the Rees name on a lot of stuff. F-R-I-G-Y-E-S, Fritz, basically in Hungarian. So that's the space. And here are some vectors in that space. Okay, a whole bunch of them. There's a distance function here. You take the difference in coordinates, square them, and add them up, and take the square root. So what's the distance between these two? If this is V1, V2, V3, the distance between V1 and V2 is the square root of 2, right? The distance between V1 and V3 is everybody's the square root of 2 apart, right? Okay. So I claim this space, this set of these things, as we go off to infinity there, the set of those things is bounded. No two are more than the square root of 2 apart, right? So if I sit on one and reach out with radius square root of 3, this is a metric space, radius square root of 3, all the others are in there, right? It's bounded. But it's not totally bounded. Because if I have epsilon equal 1/2, how can I cover every one of these things with a metric ball of radius 1? I would have to use one to cover him, use one to cover him, use one to cover him. They're all this distance apart, so nobody is not crowded in any of these metric balls, right? There's one of these things in each one. So we have infinitely many required. That's not an epsilon net. An epsilon net is a system of metric balls of radius epsilon, finite in number, that covers the set. It isn't going to cover that set. Even though the set is bounded, it's not totally, which means it's not compact. It would be complete. L2 is complete, but not totally bounded, so it's not compact.
Can you say that one more time about the epsilon net?
Oh, an epsilon net. This gets back to the Lebesgue number. It's very close to that. An epsilon net is a system. The context is metric spaces. An epsilon net is a system of metric balls of radius epsilon that they're open and they cover a given set. That's an epsilon net. Being totally bounded means for any epsilon, an epsilon net exists. And the problem is, when epsilon gets small, you need more than finitely many of these open metric balls to cover the set, and then you've lost the total boundedness. So anyway, there you go. Continuous image of a compact set is compact. Oh, let's prove that one too. Okay, so I have a compact set here, K, in the space X, right? And I have a function f that's continuous and another space Y. So over here I have f of K. That's some other set, right? K is compact. I'd like to show f of K is compact. That's a continuous image of a compact set. Okay? So suppose this is any cover with open sets of f of K, right? I'm covering the hell out of f of K. All of them. All right? Could be grossly uncountably many sets. Each one of the open sets that I have used here has a pre-image. So let this be O sub alpha is just one of them. The cover will be O sub alpha alpha in some index set, and this could be huge. But O sub alpha, if I bring it back with the inverse set image, this doesn't have to be an invertible function. This is just the pre-image. Right? Every point in O alpha has at least one predecessor here. So I'm going to bring it back. Okay, so what does that do? A continuous, remember this, a continuous function is a function such that the pre-image of an open set is open. That's the fundamental definition. That's the topological definition. Pre-image of an open set is open. If you adapt that to the reals or metric space, you can get into the epsilon delta business. That's all it really is. The epsilon delta business was first, and then the notion of the topology second, but then the topological definition is so much simpler. But these theorems just happen easier if you do it in the more general case of it. So I bring back an O alpha, and what happens? The O alphas, the pre-images, all have to cover K, don't they? How could it not? If something was left out, then there's a forward image that would be left out over here. Okay, K is compact. So only finitely many of these are required. Take the forward image. Doesn't that cover everybody over here? Anybody that was in here is covered, so it gets covered over there too. Therefore, that was arbitrary. We now have extracted a finite sub-cover is compact. So a continuous image of a compact set is compact. It's a hugely important theorem. True.
What's the name of the theorem?
A hugely important theorem.
Well, usually important theorems having names that you remember.
I'm not sure. It's more of a lemma, really. Continuous functions conserve certain properties like connectivity and compactness, and not others.
Well, what Rolle's theorem?
Yeah, bounded set. A continuous function doesn't preserve a boundedness, but it preserves things like if you're bounded and closed, it preserves that, because that will be compacted through reals. A closed subset of a complete space is complete. Absolutely. True enough. Why is that? You have a complete space. That means every Cauchy sequence converges, right? So if I have a closed subset inside all limit points, since it's closed, that means you contain all your limit points. So if you have a Cauchy sequence in here, it converges in the big space outside, right? But then the point that it converges to is either inside or outside. If it's inside, you're done. If it's outside, you say, well, that's a limit point of the Cauchy sequence inside the set, and since it's closed, it must contain its limit points, so it must have really been in there to begin with. There can be no limit point of a Cauchy sequence in the closed set that isn't already in it, right? Denny's criterion asserts uniform continuity. False. It's not right. Doug's going to tell us why.